And everyone, it's about time for class to start, but let's go ahead and see if anybody has any questions for me. You can just speak up if you have a question. You can go ahead and chat me your first and last name so that I'll have that as a roll. Mr. Gooch, I discovered that you have a cousin in my class. You told
Professor, one
Yeah.
thing that I had a question on was on the Canvas page under where the syllabus is.
Mm-hmm.
It looks like there's like multiple syllabus or syllabi.
I
Uh,
think both of them's acceptable.
yeah. Um, and I was just curious, like I've opened them on Word and some have like a slightly different word count and stuff. So I wasn't sure if like maybe they're for different classes or if there's just one to mainly pay attention to.
So what happened was there's one that's called PHY 241 N02B syllabus. That was the original one I made.
Okay.
And I found errors. So instead of the word syllabus, the next file has 090224. And then I made other errors, found other errors, and the latest one ends in 090624. That's the correct one.
Got it. Perfect. All right. Sweet. Thanks.
If I make any other changes, they'll have later dates, and you always know which one's the latest date is the correct one.
Okay.
That
Cool.
makes sense. Now,
Yeah.
I also, y'all might be chomping at the bit wondering about this, but according to our syllabus, of course, we had a test that was due today. Of course, I moved it back because we missed so many days or whatever, but now that online test is due a week from today. So it's actually at midnight on Sunday is test one, which is an online test. The way it works is, remember, each time you take it, you'll get slightly different questions, but you're allowed to take it. I think I gave you 3 attempts and only the highest score counts. And it's supposed to be done by 11:59 p.m. on Sunday. Okay. Again, like I said, it'll only cover chapters 1 and 2. It's got the equation sheet. It's got the covers, the inside cover of the back of the book. It's got a periodic table in it. And like I said, you can take it up 3 times. You're allowed to use open book, open notes, open other books, open other people's notes. The only thing you're really not supposed to do is, in principle, if someone had a chance to see the test, like now that it's open, any of your classmates might have already taken it once. If any one of those people had actually seen the test and then started writing notes that are even remotely related to that test, if you then looked at those notes, that would be cheating. Or if that person made an internet website or something and you looked at that website, that would be cheating. But other than that, it's not cheating. So you can Google, you can look for Chegg. I advise you that I tried to make the time small enough where you could look up one, maybe 1.5, and not lose any points. I've stopped trying to do that because I discovered some people work so much slower that they almost were forced into cheating. So I just want you to rely on your own discipline, because it's only going to harm yourself by if you have to look up more than one, you're probably not ready, and it's going to be a bad day when you get to the first face-to-face test. So use that as a guide. If you've been taking the practice test and consistently scoring 80 or better without looking any up, or maybe looking up one every 2 or 3 attempts, then you're probably good to go. But if you get there on the test and then you find out that I had to look 2 up, then you know you weren't ready. So you need to study some more before you take the test. There will be one due Sunday, and then the following Sunday, another one will be due. And they're really, like I said, they're more of like a really quick extension of homework. Most students finish them really quickly. You should be getting close to 100. If you don't, that's okay, but you should be, because you have access to everything. And I expect you to get close to 100. That's fine. Okay. Anybody have any other questions before we get started?
Yeah, you said you knew my cousin. Was it Jake Haley?
Yeah, it's Jake. You got another friend coming to look at you too. Someone I guess you know from Region or whatever. One of my students in my class, Cage Lackey.
Oh, yep. He goes there too. Yep.
Yeah, yeah, they were all talking today. We were talking about the Big Bang and what we know about cosmology and dark matter and dark energy. So fun group. But anyways, yeah, Jake told me that you had I had his cousin in my class. So anybody have any other questions about anything? And Andrew's picking out having him some supper right now. Yeah, Jennifer, go ahead, huh?
When is the homework due?
I moved
Chapter
all the
3?
dates back. So again, never pay attention to the Pearson homework. Never pay attention to the due dates on Canvas. Always go there. I think I've moved even the one that was due yesterday. I think I've moved it due to Wednesday. So you've got a little bit more time on chapter 17, chapter 18. Are you the one that sent me a text message, by the way, Jennifer? About chapter 17? Okay. Somebody had sent one. I think I replied, but I'm not sure. But anyways, I think I moved chapter 17 to be, no, chapter 18. I think I moved that to be due Wednesday. We've done all of chapter 18, all that I'm planning on covering. You, of course, can look up more on the my YouTube channel, but we're going into chapter, or excuse me, that was chat 242. I'm sorry. Yeah, slightly different class. Okay, so y'all ready to start doing some differential equations with curls and yeah, sorry about that. Yeah, so chapter 1 and 2, I know I made chapter 2, I think, due Wednesday, and chapter 3 is not due until Sunday this weekend.
I didn't miss anything but questions, did I?
Yeah, nothing really but questions.
All
Yep.
right, cool. I was stuck in traffic for a bit.
Yeah, you didn't miss anything. You know me. It looks like most people have already chatted me your first and last name. There's only one Miguel, so what you did was fine, Miguel. But if anybody hasn't chatted me, go ahead and do that so I'll have you for attendance. I'm going to go ahead and jump into chapter 3 now. Like I said, do refer to the Pearson site to check your due dates. But I did, like I said, I did push the chapter 2 back. I think I have given y'all today and tomorrow, I think, is all you've got left to do chapter 2. But chapter 3, you should have till Sunday. And evidently, this Jesus is coming behind Jennifer. I don't know what it is. Oh, okay. I see it's a star balloon by a light. I was like, there's a light and it's getting bigger and bigger behind her. Ah, there you go. All right. So what I'm going to do is share my screen with you guys, and we're going to start talking about vectors because they do evil with direction and magnitude. So that's where we're going here. All right. And now if I can open my iPad, that'd be awesome. Okay, now if I can, I hate it when it does that. Okay, so it should be coming up any minute now. So the first thing I want to tell you is, yes, Vector was right when he gave us the definition of a vector. It is a quantity that has direction and magnitude. And right now we're not dealing with vector fields. So right now, vectors are just these things that we put in space, and they don't change because we move to different points in space. Their effects might change. Like if you take a force that's, at a certain angle, at a certain magnitude, and if you put it on the center of a 2x4, it's probably going to push that 2x4 in some direction parallel to itself. But if you put it at the end of a 2x4, then it's probably going to cause it to rotate. So the effects can be different from place to place, but the main thing is the vector itself doesn't change from moving from one place to the next. So that's going to come in handy to us later when we talk about more complicated things called electric fields or vector fields in general. That means an assignment of every point in space, x comma y comma z in parentheses. That's a point in space. If you assign to each one of those points in space a vector quantity, then if you pick up a vector and move it from x1, y1, z1 to x2, y2, z2, then the vector might be entirely different. There's a while before you have to deal with that, though, so don't worry too much about it. I just wanted to warn you that's where we're headed. So what we have now is the idea that a vector is something that has direction and magnitude. And I will tell you that if you consider it to be arrows, like drawn arrows, it actually works. You can actually mathematically prove that a vector, which is an arrow drawn in space, is what we call part of a vector space. And if you define what addition is and subtraction is and all that stuff, there's ways you can go about proving that a arrow is a vector and it's in a vector space. That being said, we don't care about that stuff. That's what you'll get in linear algebra and some other courses, group theory, stuff like that. So with that idea that we're starting with a vector as a arrow, we just got to remember that when we go to place the arrow, for instance, on graph paper, that we want to be cognizant of its direction and its magnitude, and we don't change them. Okay. Additionally, we want to draw it to a certain scale. So when you're drawing a vector that might be, say, 150 newtons, or a vector that might be 150 meters per second, or a vector that might be 150 meters per second every second, and it's going to be at 30 degrees, then it's always going to be 30 degrees. It's always going to have a magnitude of 150. But you might put it on paper and decide that you're going to use the scale that the 150 Newton vector will have a length of 15 millimeters or 15 centimeters even. That's okay. That's a good scale. And notice how the 15 is a multiple of 150. So that works really nicely. It doesn't have to be a perfect multiple. It just has to be a multiple. So you could make up a weird scale like 1 Newton is 3.24 millimeters. And then you write that off to the side, and you might even write it as 3.24 Newtons equals 1 millimeter on paper. You might even say the words on paper, because you will need to readily be able to convert back and forth between what's on paper versus what's in reality in space. So we call one the paper space and the other one we call the space. Okay. So just keep that in mind. If you guys are actually in engineering, are many of you in engineering, or most of you in something other than engineering? No easy way to really answer that in this forum unless you just shout it out. So you're welcome to shout it out.
Engineering. Yeah.
You are engineering. So the reason why I asked that is, and hopefully your instructor might have already told you, you're allowed 4 years of free AutoCAD use as a student. So my daughter took a whole year of drafting, and about 3/4 of the way through, I discovered that she had the ability to get a free copy of AutoCAD for her computer, and she didn't know it the whole time. So she'd not been doing very well in the class, all because she didn't know that she could have it to practice with. So I want to make sure you guys know that. Now, as an engineering student, if this is your first year, I would not waste my one of my 4 years with Autodesk by doing it this year, but I definitely do it by the second year. And the reason why I say that is AutoCAD allows you to draft vector diagrams at a perfect scale. In other words, whatever scale AutoCAD makes for you is just fine, but it's going to get exactly right answers. Whereas when you do it graphically with T-squares and protractors and straight edges and rulers, you're probably going to get, if you work really hard and use very precise sharp pencils and all this stuff, you could probably get around 1% error. If you do it really precisely with AutoCAD, you're going to get 0 error, 0.00% error. Okay. So that's something to keep in mind. That means you can always draw a system of vectors and then draw a result, and from that figure out what the right answer for vector addition is, or vector subtraction, or vector cross products and all that stuff. So we're going to make use of that to some extent, because I'm first going to recognize that in thinking about vectors and treating vectors as if they're arrows, if you imagine your house like in a Google Earth picture or something like that, and you walk out onto your front porch, you could then put a dot right there on the front porch to represent where you are right now. And then you go on a walk. You might walk due east for a few feet and get to the curve, at which time maybe you're checking the mail or something. And then you walk due north a different distance. And when you come to a stop at that different distance due north, the arrow that points from the mailbox to that new point is your new displacement vector. Your old displacement vector was the arrow that pointed from your porch to your mailbox. And if you draw a vector from the dot on your porch to the dot north of directly in front of your house, then that would make a vector that is really your displacement over two trips. And in fact, that is the sum of the two trips that you made. So let me show you what I mean by that. So let's say, for instance, this is your house. Okay. And let's say this is your front porch, and that's where you were standing. Now, you might have walked down the sidewalk or the let's say the walkway out to your front yard and to the sidewalk. Let's say you live in the city, so you actually have a sidewalk in front of your house too, and maybe this would be the curb. Okay, and maybe your mailbox will be right there. So your first trip might be a walk from here to here, and I would call that vector A. Now, the length of that arrow is in some sense directly proportional to the magnitude of that displacement vector. Like if that distance was 50 feet, then I might use 1 centimeter equals 10 feet as my scale. And then I draw 5 centimeters out, and that would be my vector. Now, you took a trip from there due north, let's say this far, in which case that displacement vector is the displacement that you took from the mailbox to that point north. Okay. Now, your total displacement after displacement A and B is really the sum of vectors A and B. That's what I mean by these arrows being the archetype of vectors. So I can now draw the resultant vector. Notice I called it resultant, and I'll label it R, but resultant is the word that we use for the sum of vectors. So if you add two vectors or 3 vectors or 50 vectors, the sum of all those vectors will be called the resultant. I'm going to say that this green vector is the resultant vector R, which is equal to A plus B. Now notice I wrote R as a capital R with an arrow over it. That's normally what we do in physics. We usually use capital letters, not always. Sometimes you have to use lowercase. Sometimes they use Greek letters and make them vectors. In your textbook, they usually don't use arrows. Some textbooks do, but your textbook does not. Your textbook uses bold print, as most of them do. So if you saw an R or a capital A or a capital B and it was bold print, there's a good reason for you to believe that that's probably a vector quantity. Now, what I just did was I drew a displacement vector A that was the displacement that you followed from the porch to the mailbox, essentially. And then the displacement vector B went from that spot where you check the mailbox to that point north of it at the end of vector B. That's your second displacement vector. And what I'm telling you is if you draw a vector from the tail of the first vector to the head of the last vector, then that is the sum of the two vectors. So notice vector A has a head and it has a tail. The tail is where you started, and the head is where you started your trip to the north. So I'm pretending, even though I didn't state it ahead of time, I'm pretending like that is the north direction. This is the east direction. This is the west direction. And this is the south direction. Does that make sense to everyone? So since we've noticed that vector A's head is the same place as vector B's tail is, then these vectors are called head to tail. So when vectors are head to tail, then the sum of any number of vectors is a vector drawn from the head, or excuse me, drawn from the tail of the first vector to the head of the last vector. So I said any number. In this case, we happen to do the number being 2. Okay. So I drew a vector, an arrow from the tail of the first vector, which was A, to the tail, to the head of the second vector, which was B. And both vectors A and B are what we call head to tail. So that works fine. Now, you might also notice that I could have instead drawn vector B first, which would be equivalent to basically, instead of you walking off the porch due east, what if you walked first due north? If you did that, then I'm going to write it in blue just so it'll stand out a little bit. So this would be my B vector. And then this vector would be my A vector. Okay. So from that, we can automatically see that vector A plus vector B is equal to vector B plus vector A, which means they're commutative. So that's the commutative property that you learned in pre-algebra about numbers. A plus B is equal to B plus A. So we've already figured out something just by treating this archetypal example. Not only that, there's another way you can think about it. Let's draw, for instance, vector A. I'm going to draw it in red again, and I'm going to draw it from here to here. There's vector A. Now I'm also going to draw vector B, but I'm going to put it tail to tail. And of course, that's about 1, 2, 3 and a half and a half. So 1, 2, 3 and a half and a half. So that's vector B right there. And these vectors are tail to tail. Now, you notice that I tried really hard to draw the A vector identical to the first A vector I did, and I tried very hard to draw the B vector identical to the first vector I did as well. So you can see this is my attempt, which if I took the time to make sure I used a protractor and all and a good measurement and everything, these would be exactly right. But we already know that, in fact, in the previous example, we had put B right here. And if that's the case, then you can automatically see that the sum of these two vectors has got to be that vector R, which equals A plus B. Now, what I realized by drawing that B there is I could have, because I told you guys, as long as you don't change the length of the vector and as long as you don't change the direction of the vector, you're allowed to move it around anywhere you want, at least right now at this early stage in your education. So I can take and imagine B as if it has a little axle or a rail that it rides on, and that little axle or rail is the vector A, and it's got this little loop, if you will, that is wrapped around A. So as long as I keep B from changing its direction this way or that way, and keep it from being stretched or compressed, then I haven't changed B at all. So I'm just going to imagine sliding it to the right, and boom, there it is where that dashed B is. Does that make sense? Now I could also take A and imagine that little loop on the end of B. I can imagine that's actually on A, and that B is a rail or an axle for A. So I could just slide A upward, and then I would get A vector up there. Okay. So we've now determined another rule for adding vectors. So when vectors are head to tail, that was what we did earlier. Now I'm going to do tail to tail vectors. When vectors are tail to tail, we complete the parallelogram and draw a vector from the common tail to the opposite vertex of the parallelogram. So notice if I had A and B like I have them here in red, then completing the parallelogram would involve me sliding that B to the right to where the dashed B is, and then sliding that vector A up to where the dashed A is, and then I've completed the parallelogram. And according to the rules, all I have to do is draw a vector from the common tail, which is this point right here, to the opposite vertex, which is that point opposite. Notice this one's actually touching one of the vectors, so that can't be opposite. This one's touching one of the vectors, so that can't be opposite. So it's got to be this guy that's the opposite. So I draw it from the common tail to the diametrically opposed vertex, and that's the sum. So that's how you add vectors graphically. If they're head to tail, you draw it from the tail of the first to the head of the last. So here's the tail of the first to the head of the last. If they're tail to tail, as you see these are, then you complete the parallelogram by moving B over to here, and then by moving A over to there, and then you draw from the common tail to the common vertex, which is that right there. Okay, so like I said, if you took the time to use like really good paper, specifically maybe graph paper, you could then have a ready representation of the x-axis and y-axis at each one of those little vertices on the graph paper, and that would help you keep everything straight. And then you just use a protractor to write out the angle and measure it out, and then draw a dot for the thing to go through for that angle. And then you shorten the drawing to the scale that you've chosen for the scale for the drawing of the vectors. And then you have a scale representation of the addition of vectors. And all you have to do is then draw it out. And all you have to do now in completing that parallelogram, for instance, is I can measure this length from here to here. I'd measure that in like centimeters or millimeters. Then I use the scale that I used to make the thing. I would use that to convert it back to real space instead of paper space. And that would be the magnitude of the sum. And then I measure this angle right here, say. Of course, I could also measure this angle if I wanted to, but I would probably choose to measure that angle. And I would measure that with a protractor, and that would give me the direction of the vector. Notice I haven't done anything talking about X or Y yet. In principle, it would be really smart for me to go ahead and make coordinate axes, so an X-axis and a Y-axis. If I did that, though, the smartest thing to do would be make one of these vectors at least parallel to one of the axes, so I don't have to do so much work. Because if I made my axes, for instance, like an X-axis this way and a Y-axis that way, then obviously A vector would have an angle and B would have an angle. So I'd have both of the vectors having X and Y axes. Or X and Y components. That would not be an easy way to deal with it. Now, I've only shown you how to do it with two vectors, but there's another thing that comes from all this that you can see. For instance, if I did two vectors head to tail like that, then I'd get the sum, which is this guy. And now I could add a third vector just by drawing the vector from the tail of the last vector to there. So this is the new vector I'm adding. And now the new sum would be from the tail of the first to the head of the last. Right? Well, with that and thinking about that, you could probably convince yourself that if you added A and then added B, after you were done with that, you added vector C like I just showed you. Well, it turns out you could have also said, I'm going to add vectors B and C together and then add A to that. So that's like our associative property. So you can see that not only does the order not matter, but the groupings doesn't matter either. So we've learned some valuable things already just from piecing together how vectors behave, at least for specifically how they behave in terms of this displacement vector. And like I said, the displacement vector is an archetypal vector, so it shows us everything we need. If we had 4 vectors or 5 vectors or 52 vectors, all we have to do is keep adding them head to tail, head to tail, head to tail, head to tail, head to tail. And when you're done with the whole loop, which could end up looking like this, for instance, we could have this vector, 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 and this vector. So that could be A, B, C, D, E, F, G, H, and I vector. Now the resultant would just be that vector. Okay, so that's what you do if you had them to label. And the trick of doing that is at the head of each vector, you would want to draw another coordinate system exactly parallel to the first one. So for instance, here's your x-axis and here's your y-axis. That just gives you something to measure with respect to. So if you go at the head of vector A and you draw an axis that's exactly parallel to the x-axis, then that'll be your x-axis again. And then you draw a y-axis that's exactly parallel to your original y-axis. Then you could use that new axis to figure out the angle and keep using the same scale to figure out the length of the vector. Then after you put down B, you draw another coordinate system here and here, and then another one here and here, and then another one here and here. and so on and so forth. That's all it takes to add any number of vectors graphically. Okay. And then you can just, of course, measure this and measure that length right there, and that'll give you the magnitude and direction of the vectors. Does that make sense to everyone? That's all graphically, and you should probably do maybe 4 of those at most. That's probably enough, and convince yourself that you get close enough by measuring it out and seeing what your resultant and your angle is, and then doing it numerically and seeing what the right answer is, or doing it with AutoCAD and seeing what the right answer is. Okay. Because this is a skill that's not going to go away. And sometimes it's just easier to do it graphically. Almost never, but sometimes it is easier and you can avoid a lot of problems. I heard somebody talking. Does somebody have a question? It's okay. Somebody might not have had their microphone muted, and that's fine. It's not a big deal. It wasn't interrupting or anything. All right. Now that we have that idea, now that was just tail to tail, or head to tail, excuse me. In principle, you can also add vectors that are tail to tail in a similar fashion. What you'd have to do is draw the first 2 vectors that you want to do. And since this associative property is in effect, you could draw, if you have vectors A through I like we did before, I could draw A and I first, tail to tail, and then complete the parallelogram, and that would give me like R1, and I just keep a track of R1 means A plus I. Now I draw another vector, maybe this one will be H, or maybe it'll be B, it doesn't matter. I can just draw that, and then I complete the parallelogram between it and the R1. And then after I do that, I pull another vector from the list and do tail to tail parallelogram with R2 and let's say vector C. But you just keep doing that, and then slowly you can get all of them. But trust me, if you're really doing several vectors, it's probably just as easy, if not easier, to put them all like I did to the left there. In other words, doing them head to tail. Just know that you could do it tail to tail as well. Okay? Does everybody understand, at least in concept, what we're doing here? Okay. Anybody have any questions on that? Does any of that look really confusing? Okay.
So, Professor, just on the head to tail part. So you're just, if you draw, say, vector A, you said you're just drawing an X and a Y axis to find out simply the length of vector A.
Exactly.
And then for tail to tail, you'd just be drawing a lot of parallelograms for that path that you.
Exactly, which would be a pain in the butt. That's why you probably do head to tail. But yeah, it always works.
Okay.
And it actually be really fast with AutoCAD because there's a way with AutoCAD you can actually type in the magnitude and direction, and it just makes it for you automatically. If you know your fast keys with AutoCAD. It's been a while since I've used AutoCAD, but it got really I got really fast by doing it that way. But that was when I was doing engineering work, not physics. Now that we have that, okay, so I get this. What I want to talk about now is ideally I'd like to just jump into another example, but I really need to explain how we could make some sense of vectors. And what I'm going to do is I'm going to introduce you into a couple concepts. What I first want to do is talk about scalar multiplication. So let's say scalar multiplication. You know, when you say multiplication fast, you can pretty much spell it wrong if you're not paying attention. It's multiplication. I was going to leave out that L. That L didn't seem right at all. And then I wrote it and I'm like, yeah, I got to have that. So with scalar multiplication, what I mean is, let's imagine you had a vector. Let's say the vector will be vector A. Okay. I didn't make that very big. Let me make it a little bigger. Okay, that's just the worst looking thing I've ever drawn in my life. All right, let's go back again. Let's say this is vector A. If I wish to multiply vector A by 2, then I'm trying to form the vector 2A. What I'm going to tell you the vector 2A is a vector that doesn't change its angle at all, but is now twice as long. So that's what vector 2A looks like. Notice it's like at that perfect 45-degree angle. That's why I'm using the little squares on my graph paper. If I wanted to draw, for instance, vector 3A, then that one would be a vector from here through here through here. Does that make sense? So if you multiply a vector by a scalar that's bigger than 1 and positive, then all you're doing is stretching it. If you multiply it by 1, what do you think is going to happen to it?
Stay the same.
Yeah, that's because those rules that we learned in pre-algebra, 1 times A is A, right? Those goofy rules are exactly the rules that have to be true for something to be a vector space. And that's where the whole concept of vectors is going, is you're ultimately trying to learn about what we call linear algebra, which is the study of vector spaces. Okay. Now, I'm sticking with positive numbers still, but now I'm going to try to multiply A by a number smaller than 1. So in this case, let's say 1/2 A. As you might suspect, that is 1/2 A. So notice I went about half the length from one corner to the other. It actually should be exactly half the length, but it still has the same angle. Okay, so that makes sense. These are all the same angle too. So I'm going to say that's the angle. I'll put this line on it. That's the same angle. That's the same angle. And that's the same angle. Notice I just chose an arbitrary line to measure it with respect to. As long as I stick to the same line to measure it with respect to, then that line's fine. I could have drawn it, I could have drawn it, for instance, right here if I wanted to. Or I could have drawn it right here. Or I could have drawn it right here. Doesn't matter. As long as I consistently do so, it will be fine. Now, if I wish to draw negative A, the only difference with negative A is if you multiply by a negative number, you have to turn it 180 degrees. So this vector is going to be like that. And negative 2A, of course, will be like that. And negative 1/2 A could be like that. Of course, it could also be like that. The main thing is half the length and pointing in the opposite direction. So that's what happens when you multiply by a negative number. It just completely reverses the direction by 180 degrees. So you can just say, hey, if the angle is 12 degrees, now it's going to be 192 degrees. You could also do theta minus 180. That would be acceptable as well. Sometimes you'll see it's better to do theta minus 1, because if you're like at 280 degrees, if you add 180 to it, you're going to get way outside of 360, and you're not necessarily going to recognize that angle. But if you subtracted 180, you'd say, oh, well, I'm back in between 360 and 100, or 360 and 0, so that angle makes more sense to me. So does that make sense to everyone? All right. So now that I have that, I'm going to use another rule that we learned from pre-algebra that looked really stupid. It was probably the dumbest rule. I remember thinking to me, why did they say this? This is the stupidest rule ever. Okay. But now it's going to make really good sense. So if I draw two vectors, let's stop making them 90-degree angles because that was a little too convenient. I'm going to draw this vector B right here, and I'm going to draw this vector A right here. They're supposed to be straight lines. Obviously, that's a little crooked, but that's okay. All right. And what I want to know is, what is D, which is defined to be A minus B. So now what I'm going to do is give you the definition that defines subtraction. So I'm going to separate this with a triple equals. The triple equals means defined as. So that's why I did it for D. In other words, whenever I use D, it's either a vector that I called D or it's a representing a difference. So it's a subtraction problem. So in this case, I'm going to say the definition of A minus B is the vector A plus the opposite of B. Okay. So now that you've experienced what it means to multiply a scalar by a vector, can anybody tell me what the opposite of B would be on this diagram of AB that I just drew? See, I have over here, I have A and B. How am I going to alter B to make it negative B?
Just draw it in the opposite direction.
Exactly. So what I'm going to do is I'm going to put the arrow head at the opposite end, and then I'm going to draw the body of the vector there. And now I'm going to write next to it negative B. So anybody that looks at it can see, oh, he's saying the blue one is the B and the green one is the negative B. Now, the rule was that A minus B is the same thing as adding A to negative B. But notice I had two vectors that were tail to tail. Did you see B and A were tail to tail before? But because I now reverse the direction of B, now they're head to tail. So we should be able to readily add them by drawing a vector from the tail of, it's supposed to be the tail of the first to the head of the last, but the commutative property says that doesn't matter. I'm just going to draw the vector from the tail of one to the head of the other. So what I'm going to say now is this vector D is equal to A minus B. So now you see that when two vectors are in head to or tail to tail position, they're really easy to subtract. I don't have to draw a parallelogram like I do when they're tail to tail and I'm adding. Now let me draw one where they're head to tail, and you're going to see the problems associated with that. So let's say A. I really cannot draw a straight line today for some reason. Bet you I can this time because I'm going to cheat. Yep, dig will. So that vector right there goes to that corner, and that's going to be my A vector. I don't like how that turned out. That makes me still a little bit angry. Okay, let me do it again. Okay, there's my vector A. And now at the head of that, I'm going to draw vector B so that they're head to tail. Okay, so there's vector B. Oh, and I forgot to take it off and make my drawings pretty. So that's vector B. So now I want to know what is A minus B again. So I've got the A, I've got the B there. What we know is A minus B, is equal to A plus the opposite of B. Now notice how much of a pain in the butt this becomes. When I put B, when I put the arrow at the opposite end, negative B is all of a sudden a big pain in my butt. Because now I've got the vectors head to head. That doesn't mean anything to me, right? But there's a couple ways you can fix this. You can, for instance, continue this line. I don't know what's happening there. So notice that line's parallel to B and negative B. Or I could also do it like that if I wanted to. Either way doesn't matter. You're allowed to move the vector around as long as you don't compress it, stretch it, or change its angle or direction, right? So what we can now do is I can say B, the negative B, in fact, is this vector right here. And I'm trying to make sure it's the exact same length as that other one. It looks like I might have made it a little too long by accident, but you get the main point, right? So now by sliding that vector along this way, I have A and B are in head to tail position, which is good because I need to add them. So I'm going to put the symbol for A back over here somewhere. Let's put it right here. Okay. Now, since the vectors are head to tail and the order doesn't matter, we know that the vector drawn from the tail of one to the head of the other is in fact the difference D equals A minus B. So that's how you add them graphically, or in this case, subtract them graphically when they're initially head to tail. So notice head to tail was easy when we added, and tail to tail was a pain because we had to complete the parallelogram when we added. When we're doing subtraction, tail to tail is easy because I don't have to complete the parallelogram, but head to tail is a pain in the butt when I'm subtracting because I do have to. Now, the other thing I could have drawn was instead, I could have moved negative B over to here. And then you'd see negative B and negative A. And you could just draw again from the tail of one to the head of the other. And when I did that, oopsie, wrong thing. When I did that, I now got D. Ooh, that's supposed to be a D. D, which equals A minus B. So if I drew all that exactly perfect, you'd see that those two red D vectors are both the same length and parallel. So does everybody understand how you could add a vector and subtract a vector, whether they're head to tail or head to head or tail to tail? Because these actually do appear occasionally as test questions. I'll have drawings like this, and you're supposed to draw them directly on the diagram, the right size, completing parallelograms and that sort of thing. And then that's supposed to be, you know, your ability to show me that you know how to add vectors graphically. All four of these are reasonable options. Now, the other way I can do it with multiple choice is I draw all the different vectors that it could be. Like I draw a vector representing A plus B, and then I draw a vector representing negative parenthesis A plus B, close parenthesis. Then I draw a vector representing A minus B, and then I draw a vector representing B minus A. And each one is a different color, and I ask you to pick out which one's right. Okay. I don't tell you that that's what they are, that they're A minus B and A plus B and the negative of A plus B and all that. I just put them all on there and you have to identify the right one. So does everybody understand what kind of questions could come out of that? Okay.
Yes.
Anybody have any questions on how that's done? Okay. So that's a bare minimum, just doing the drawing, because once you're doing them drawing wise, you can then use, like I said, AutoCAD to figure out exactly the right answer, or you can just use drafting techniques, like you draft a blueprint or something like that, and in that case, get a very close to the right answer. But now what I'm going to do is show you how we add them algebraically. In other words, with math as opposed to the other stuff. So the math way is exactly right as well. And the only errors that come from that are errors of the brain, not errors of the math or the errors. Okay. So let's go to adding. And in order to do that, I'm going to first draw a vector and I'm going to try to express to you what it means. So let's say we have a vector A, which equals, let's say the vector is 200.0 newtons. And if I specify it with the at symbol and just a degree after it, then that means something very specific. And I'm going to show you what that means. What I'm going to say is at 30.0 degrees. Now, when I say that, that automatically should tell you, oh, he's referring to what I learned in trigonometry, which would have been pre-calculus for you guys, that if I just say it's at 30 degrees, I mean it's measured counterclockwise from the positive x-axis. So that automatically tells you, oh, I've got to have a positive x-axis and I've got to have a positive y-axis, because counterclockwise means it's turned counterclockwise towards the y-axis. So what I'm going to do right quick is I'm going to quickly draw a coordinate axis in black. And then another one right here. And now this guy is going to be X. And that guy's going to be Y. Okay. Now what I'm going to do is I'm going to show you how to specify that vector. And what I'm going to do is I'm going to lay my protractor. This is my protractor, and it's got a little hole right here. That hole represents the center of this circle. And that's what's supposed to line up with the tail of the vector when you're doing this. This line that's horizontally from this hole and goes all the way to 0 degrees, and then it goes all the way the other way to 180 degrees, that line should be lined up exactly parallel to the x-axis. So when I do that, I'm looking at it right now. I've got everything lined up, and I'm going to say 30 degrees corresponds to that mark I just drew right there. So I know that is the actual direction I want to draw it. So now what I'm going to do is lay my straight edge such that I have a little bit of gap so I can hit the origin of this coordinate system, and then a little bit of a gap so I can hit that dot. So now I'm going to take my red pen. Actually, I'll do blue. Okay, I'm going to set my blue pen up. I again got it offset a little bit from the coordinate origin. I've got it offset a little bit from the dot, and I'm hoping that's enough to allow my pencil tip to go down, and it does appear to be. Okay, so notice how I drew it right through there. That means this angle right here is 30.0 degrees. Now, I've also got to decide on a scale. And I am going to say the scale will be, I think a good scale for this one might be, I'm looking at a centimeter scale laying on this real quick. I'm going to say 4 centimeters corresponds to 200 newtons. So that means it should end right there. And now I'm going to take this and erase it all the way to that point. Okay. And I'm going to write over here that my scale is 200.0 newtons in space equals 4.00 centimeters on paper. Obviously, this isn't really paper, but you get what I mean. And now I'm going to put a little arrow on it just so I remember which end's the right end. Okay. So this is my vector A. Now, in order to work these problems out, what we want to do is build a right triangle out of that vector. So to decompose vectors, we create a right triangle such that this is a nice mathematical symbol. See that little thing? That's supposed to be like the cursive S followed by the cursive T. So it saves you a buttload of time when you just write that instead of such that. So such that one leg is parallel to the x-axis and the other is parallel to the y-axis. Okay, so the way I'm going to do this is I'm going to make a right triangle, and one way I could do it is go parallel to the x-axis until I get directly below the tip of the vector, and then I put an arrow on it like that, and now I draw another one parallel to the y-axis. I could put it head to tail. That's the way I like doing it, and that's what I'm going to do. So this vector right here is called a sub y, and this vector down here is called a sub x. And notice it is a vector, so I have to actually write vector symbol over top of it so that everybody knows it is a vector. You're not supposed to, for instance, have like here where I said r is equal to a plus b. It's not okay to have r vector on one side equals a plus b on the other side unless a and b are both vectors. So you're never supposed to have a vector equals a scalar or a scalar equals a vector. So that's something that you need to keep in mind as well. Now, from what we know regarding trigonometry, we know, for instance, that the sine of 30.0 degrees is equal to, remember, it's so toa, or I use some old horse came hopping through our alley. Either one of those is fine. But the main thing is this says sine of theta is equal to opposite over hypotenuse. And with a right triangle, the right angle, see this little square right here? That looks like an arrow that points to the hypotenuse. So that'll keep you straight as to what's what. And then the opposite angle is the angle that's not touching, or excuse me, the opposite side is the side that's not touching the angle. And the adjacent side is the side that is touching the angle, but it's not the hypotenuse. So I can say sine 30.0 degrees is equal to the magnitude of a sub y divided by the magnitude of a. Okay. So this tells me, for instance, that a sub y, notice it is positive, and I'm always going to want you to create that sign yourself. I don't want you letting the trig spit out the right sign, because there's a lot of ways that calculators can give you answers that'll screw you up. So you're going to force the sign, whether it be positive or negative. According to this, AY will be equal to A times the sine of 30.0 degrees. And that, of course, is equal to 200.0 newtons times the sine of 30.0 degrees. And of course, there is a special triangle, the 30, 60, 90 triangle. And when you use that, you can avoid actually using your calculator. So that's something you can do. And I occasionally do it in my class. So just be prepared for that and don't get, hurt by it. So now I'm going to take 200 times sine 30. And that gives me, of course, since the sine of 30 is 1/2, that gives me 100.0 newtons. So that's what the y component of that vector is. Similarly, cosine theta is equal to adjacent over hypotenuse. And remember, adjacent is the angle touching, or is the side touching the angle. So now I can write cosine 30.0 degrees is equal to a sub x. Notice how I just wrote a sub x without the vector symbol, and that's another way of writing the magnitude. I can write it with the vector symbol by putting absolute value bars around it, but I don't have to. So this tells me that a sub x is equal to, notice it's pointing in the positive x direction, so I'm going to force that positive sign right there. And I'm going to say 200.0 newtons times the cosine of 30.0 degrees. And that's going to equal 200 times cosine 30. That gives me 173, whoa, Nelly. 173.20 newtons. Okay. So that's what it means to decompose a vector or to break a vector down in its components. Obviously, when you're not given an X and Y axes and you have to draw your own, it's almost always smarter to make one of the vectors lie right along either the x-axis or the y-axis, so that at least that one vector has no component in the x direction or the y direction or something. So that's just a handy hint that helps you a lot of times. It's never wrong. You can choose any coordinate you want. In fact, you could have 4 vectors at 0 degrees, 90 degrees, 180 degrees, and 270 degrees and add them all together, and that works fine. But when you go to break the components, if you actually chose to put it the x-axis tilted at 45, then every one of your vectors would have an x and y component, when you had the chance of every one of your vectors only having an x or a y component. So really, it's sort of self-defeating, let's put it that way. All right, so now that we have that, what I'd like to do is go ahead and add 4 vectors. So,
Professor, could you say that one more time? You said it was easier to decompose a vector by
if
doing
you
what?
choose one vector to lie directly along an x-axis or a y-axis.
Okay, got it.
So adding 4 vectors algebraically. So the first vector I'm going to specify is the A vector, which is 200.0 newtons at 30.0 degrees. Okay. That's a typical way of actually expressing a vector. In fact, the normal way that most people do is they give you a magnitude and direction. Now, in order to do what I'm getting ready to do, I need you to understand something about coordinate systems in general and how we use them. So generally our x-axis is drawn pointing to the right and our y-axis is drawn pointing up. You can change that all you want. That's fine. The main thing is no matter what, there's still a correct way of thinking about compass headings and stuff like that. So this y-axis also corresponds to due north. And this y-axis in the upward direction also corresponds to 0 degrees as a compass heading. Well, that went horribly. So let me fix that a little bit. So it's 0 degrees as a compass heading. Okay. Similarly, X is the east direction, and that's also 90 degrees for a compass heading. The negative y-axis is south and 180 degrees compass heading. And the negative x-axis is west and 270 degrees compass heading. And we find out, in fact, that the y is also 360 degrees. 360 degrees and 0 degrees all correspond to the same thing. Okay. So now I've got vector A, and I'm going to try to do one in each quadrant so you can pick out the positives and negatives and that sort of thing. So now I'm going back to green. I'm going to say vector B is going to be, let's say vector B is going to be, I'm going to say 50.0 newtons at, now this time I'm going to say 36.87 degrees, let's say north of west. So that's a whole new neat way of doing it. Okay. And I'm trying to use this example specifically so that you can see each of the ways we do this. So for this first one, that at symbol means that I measure the angle 30 degrees counterclockwise from the positive x-axis, and then A would be this guy. This one, on the other hand, says 36.87 degrees north of west. So I'm going to draw it like this, and this is 36.87 degrees. Notice how I actually started west and then rotated it towards the north. So that's why it's called north of west. Does that make sense to everyone? Now I am going to say that we have a vector of C equals 141.4 newtons at, in this case, I'm going to say negative 135.0 degrees. Now remember, negative means you measure counterclockwise from the positive x-axis. So I'm going to go from here to here and say this is vector C, where this part right here is 45 degrees and this part right here is 90 degrees. So you see, if you add 90 and 45, you get 135. That's why I called it negative 135 degrees. Does that make sense? Okay. Now I'm going to do vector D. Vector D is going to be, let's say vector B will be Yeah, I think I like this. I'm going to say vector B is 100.0 newtons at, and this time I'm going to say a compass heading of 126.87 degrees compass heading. Okay. So in this case, it means this whole angle right here is 126.87 degrees, and that's vector D. Does that make sense to everyone? Now I've run out of paper, or room on my paper. So I'm going to steal this and copy it over to the other side. So copy. And I'm going to say paste. And I'm going to paste it over here off to the side. Actually, I think it might be better over here. I'm going to leave it right there. And what I'm going to attempt to do is draw this graphically as best I can. So actually, first off, yeah, I really want to draw this as best I can. What I need you to see, though, is if we look at this diagram, let's say green is going to represent positive and red is going to represent negative. So when I look at vector A, I have a positive X component and a positive Y component. Y'all see that I just drew that. It's really hard to draw, so I apologize for obscuring everything. Okay, but the main thing is you see that the X component is in the positive direction and the Y component is positive direction. Everybody see that? So A has positive, positive. B, on the other hand, which is this guy, this one has, in fact, a negative X component, but it does have a positive Y component. So this guy has positive, negative. I think you can see that C has negative, negative. And I think you can see that D has a negative Y component and a positive X component. So I'm going to call this positive, negative. Does that make sense to everyone? You have to imagine yourself walking parallel to the axes from the tail of the vector to the head. It doesn't matter which axis you go across first. You can walk straight down the x-axis, or you can walk straight down the y-axis in the positive direction or the negative direction. Doesn't really matter, long as 2 steps get you to the head of the vector. And then doing so, that lets you dictate whether those arrows are pointing left or right, which gives you, the negative sign or the positive sign, or whether they're pointing up or down, which gives you the positive sign or the negative sign. Does that make sense? All right, so we're going to try to go back now that I've got that. Everybody follows that diagram, even though it's a little messy, I get it, but y'all see how I was using that to figure out what my components are? So what I have to do now is, and by the way, if I was doing this in the PHY 201 or 202 course, I would advise them to make a table. It's certainly fine for you to make a table. It's just way more work than is really necessary. All I do now is go ahead and make the individual components of the A vector and make the individual components of the B vector and so on and so forth. So I'm going to start off with A vector. So A sub x, we can see that A sub x was in the first quadrant and it was 30 degrees up from the positive x-axis. So that had a positive x component and a positive y component. And we can also see that it'd be 200.0 newtons times the sine, or excuse me, times the cosine of 30.0 degrees. And we've already worked that one out. Clearly that one is 173.2. And it's positive. Okay. Now, both the 2 and the 0 are not sig figs. AY, on the other hand, is also positive, and that's going to be 200.0 newtons times the sine of 30.0 degrees. And this one's going to be positive 100.0 newtons. But because the 30 only being specified to 3 sig figs, that means our answer is going to be 100.0 newtons, with the last 0 being a non-significant figure. Okay. Now we're going to do vector B. So B sub x, if we look back at that, remember B sub x had a negative x component and a positive y component. And the 36.87 was actually measured up from the x-axis. So cosine corresponds to x and sine corresponds to y. So B sub x is definitely going to be, I didn't mean to put a vector there. So B sub x is going to be negative. Now the magnitude is 50.0 newtons times cosine 36.87 degrees. And that gives us a negative 50 times cosine 36.87, which should give us 40, and it does. So that's 40.00 newtons. So that last 0 is not good, but notice I did force the negative sign. Now the by is positive, and that's going to be 50.0 newtons times the sine of 36.87 degrees. Now that one should give 30, and it does. It's going to be positive 30.00 newtons. Everybody follow that? Ah, crap, it's 6:40 already. Okay, so it is 6:40, so my alarm did not go off at 6:38 like it was supposed to. I'm going to finish up these 2 vectors. If you guys need to split, go ahead. It's not a problem, but the recording is going to be going here. So I'm going to go ahead and go try kind of fast and then finish up the rest of this vector addition problem. It'll be on the video, so if you have to leave, it's okay. But I'm going to go ahead and hurry now. Sorry about that, everyone. So your C vector, I'm going to have a C sub x. Now our C vector was in the 3rd quadrant. So it actually had a negative x component and a negative y component. And since it was 45 degrees, I could put the 45 degree where you see it, or I could put the 45 degrees right here. If I put it right here, then cosine gives me the x and sine gives me the y, but it really doesn't matter because sine of 45 and cosine of 45 are the same. The main thing is I've got to realize that they're both negative. So negative 141.4 newtons times cosine 45.0 degrees is equal to negative. You should see that this is actually going to be 100.0 newtons negative. And then C sub y would be a negative again, 141.4 newtons times the sine of 45.0 degrees, which gives us again negative 100.0 newtons. You can check that with your calculators. You should, of course, but I know that that's the case. And then finally, we've got D vector. So D sub X and D sub Y is what we've got to figure out here. Now, if you look at D vector, you can see that the Y component is negative, but the X component is positive. So the Y component is negative, the X component is positive. So I'll put that there. Not only that, we can see that the 36.87 is actually between it and the X-axis. So if I took the cosine of it, that's going to give me the X component. So I'm going to go ahead and say 100.0 newtons times cosine 36.87. Now 20 is, or 100 is actually 20 times 5. So this should actually give me 20 times 3 basically, but you can see 100 times cosine 36.87 equals 80. So that's positive 80.0 newtons. I could put a 0.00 and then mark that last one. So I'll do that. Okay. Now dy is going to be negative. That's 100.0 newtons times the sine of 36.87 degrees. So this one's going to give us a negative answer. Okay. 100 times sine 36.87, and that gives me 60 newtons. Okay. Now, the big rule, and you can sort of see it from like trying to add them up head to tail, head to tail, head to tail. You can see that you're adding up the X components of all the vectors and then subtracting the negative X components. And then you're doing the same thing with the Y components and subtracting the Y components. So ultimately, one of the formulas we're using is R, the resultant, has an X component that's A sub X plus B sub X plus C sub X plus D sub X. And R, the Y component, is equal to A sub Y plus B sub Y plus C sub Y plus D sub Y. And of course, the general rule is the resultant is always the sum of the vectors. So now all I have to do is say R sub X is equal to 173.2 newtons plus negative 40.00 newtons plus negative 100.0 newtons plus 80.00 newtons equals 173.2 plus negative 40 plus negative 100 plus 80 equals, now because these were added, we can see that the last significant digits in the ones place. So this has to be 113.2 newtons, but that 2 is in the 10th place, and the ones place is the last sig fig. So that's our final X component of the resultant. Now I do R sub Y, and R sub Y is going to be 100.0 newtons plus 30.00 newtons plus negative 100.00 newtons plus negative 60.00 newtons. So I can automatically see that the 100 newtons cancels out with the negative 100 newtons, and I'm left with 30 minus 60 is negative 30. So this would be negative 30. Ooh, Nelly. This would be negative 30 it looks like the only one we're going to have is the ones place again. So this is 30.0 newtons, and I only have 2 sig figs for that. So that's really problematic. Now that I have the components of the vector, I could, in principle, here's another thing I'm introducing. I could say that R is equal to R sub X times this vector called I hat. I hat is what we call a unit vector, and every vector that has a hat on top of it, we use that hat to indicate that it's a unit vector. And what I mean by that is its length is 1 unit. It's not 1 meter, it's not 1 Newton, it's not 1 meter per second or 1 meter per second. It's 1 unit. So when I multiply, for instance, 113.2 newtons times I hat, I get 113.2 newtons times I hat. Okay. So that's a way I can write it. It's also plus RY times J hat. Of course, if I had a Z component, it'd be plus RZ K hat, but we don't have that, so we're not going to deal with it. I will also say that an alternative is RX X hat plus RY Y hat. That works as well. Okay. But the rule is if I gave you vectors in magnitude and direction format, then you should give them back to me, the sum, as magnitude and direction. So I'm going to now show you how to make that into magnitude and direction. So what I have to do is draw another coordinate system. So there's my y-axis, say. And there's my x-axis, say. Now, what I have is an x component that's 113.2. So I'm going to draw a vector that represents 113.2 newtons. And then it has a y component that represents, or that is negative 30 newtons. So I want to make it roughly about the same size. 30 goes into 113 about 3 times, or actually about 4 times. So it's about a quarter of this guy. So I'm going to say this is roughly 30.0 newtons. And then I can write that the actual vector, the resultant vector R, is that vector right there. And that angle I'm going to call phi or phi. Okay. So first, to get phi, I'll say phi equals the tangent inverse. Remember TOA, SOHCAHTOA. TOA is tangent equals opposite over adjacent. That would mean, notice how I'm not putting any signs in. You don't want to put signs in. Now I'm going to take the inverse tangent. So I hit shift tangent inverse parentheses 30 divided by 173.2 close parentheses. That's 2 sig figs and 3 sig figs. So I only get 2 sig figs. This is going to be 9.83 degrees. And that 3 is an extra sig fig. That's an extra digit, not a sig fig. So that's how I can get it. There's other ways, of course, to get the angle, but that's one way. And can anybody guess what we have to use to get the magnitude? Pythagorean theorem, how about that? So I'm going to say 30.0 newtons squared plus 113.2 newtons squared. Now, in tracking down the sig figs with this, this can be a little rough. I'm going to type in 30 and then square it, and I'll see that I get 900. So what's going to happen here is this quantity only has 2 sig figs, but the answer is 900 newtons squared. So that means only the tens place and the hundreds place are significant figures. Similarly, I'm going to do 113.2 and square that. And that gives me 12814.24 newtons squared. But this one only has 3 sig figs, so that means the 1, the 4, the 2, and the 4 are not sig figs. That means the hundreds place is the last significant digit. Okay. So now I'm going to take the square root of 900 plus 12814.24, and I get the answer is 117.107. Now, as sig figs go, I'm only allowed to use the hundreds place. By the way, 900 plus 12814.24 gave me I'll write it over here. It gives me 13714.24. And I said it's only good to the hundreds place. So all these guys are not sig figs, but you see, I do have 3 sig figs. That's the key point. So now I can say, oh, those guys are not sig figs. So I can finally report that my vector R, the resultant, is equal to A plus B plus C plus D, is actually equal to 117.1 Newton. Notice I underlined it to make sure I'm giving someone an extra digit in case they need it. And I'm going to say, since this measurement was made clockwise from the positive x-axis, I can just use the at symbol and call that negative 9.83 degrees. And that is my complete answer. So now I have shown you how to add vectors, and it's not unlike what I called in my YouTube channel, the world's greatest vector addition problem, because I did the same thing with that as I did here. Specifically, I tried to use each of the 4 types of ways we can specify vectors so you have an example of it. I also hit each of the 4 quadrants so you can see how I use them to figure out whether the x components and y components are positive or negative. And of course, we're done. Anybody have any questions? I'm going to stay here till the last person leaves. And of course, make sure you chat me your first and last name if you haven't already. But you guys are free to go, and thank you for coming. I'll do all the projectile stuff next time. Yes, Jennifer.
Thank you.
You're welcome. Do you have a question, Jennifer? Oh, she's saying bye. Gotcha. Yep, that's it. Stop share. Bye, everybody. Bye-bye. Bye-bye.